Hello, so this is question 3. Now, so that we can add energy to melt something, but we can also remove energy from it in order to freeze it. So melting and freezing is the same process in reverse. So in this question, how much heat energy does a refrigerator need to remove from water in order to bring it and make it into ice? So in the summer day, we a lot of time what we do is we put water in the refrigerator freezer and then we make ice with it, right? So let's say you have a 1.5 kilogram of liquid water and you want to make it into ice. So you want to make it into negative 10 degrees Celsius ice. So that, again, is not a one-step process. You cannot just do 20 degrees Celsius to negative 10 degrees Celsius. That's not the right thing to do. So what you need to do is to consider where you are right now. So we have 20 degrees Celsius water, and that is a liquid, right? And we want to bring that liquid water into 0 degrees Celsius water. Now, why 0 degrees Celsius? Because that is the freezing point. So this temperature has a specific meaning, right? It's a freezing point. So you cannot go from 20 degrees Celsius water to negative 10 degrees Celsius ice without going through that point first, right? So, I mean, yes, at the end, you are trying to go to negative 10 degrees Celsius ice, but you cannot get there directly. It has to be from water to that melting point, to that point, freezing point first, and then freezing point, melting point is the same thing, right? So, and then to the second step. The second step is to bring the water, so 0 degrees Celsius water, and now we remove more energy from it so that it becomes 0 degrees Celsius ice. And then the final step is to remove energy further from the ice so that it goes from 0 degrees Celsius ice to negative 10 degrees Celsius ice. So it becomes even colder ice, right, at the end. So it's a 3-step process because you have that freezing point. So you have to go through that freezing point. Okay, so first part is going to be MC delta T, is change in temperature, right? So mass, specific heat for water, change in temperature for liquid water. Now, this is for water. So again, this number is something that we know very well. 0.5 kilogram, and then specific heat. So this is the 4,186 joules per kilogram degree Celsius value, multiplied by the change in temperature. Now, the change in temperature is going to be V final minus V initial. So in this case, negative 20. You're actually going down by 20 degrees Celsius, right? So 0 minus 20 degrees Celsius, and you're going to get a value from there. So with my calculator, I have 125,000 joules of energy. But of course, it's negative because we are removing energy from the system in order to lower its temperature, right? So then part 2. So part 2, we need to get the water and freeze it to ice. So that is going to be called heat of fusion, right? Heat of fusion. So this is a value that we need to look up from the new table today, which is the latent heat of fusion. And what is that number again? So let's go up one page. Let's look at the chart again. So for water, melting and freezing is the same thing. So the value is 334, right? So 334. What? 334,000, right? So let's go back here. So 334,000. So 1.5 kilogram, and then 334. So 334. But the value is actually 334,000, unfortunately, and that's it. So that you can use, again, a calculator. It's negative because you're removing energy from it, right? So you're removing energy. Removing energy in order to freeze something, right? So you put a negative in front. Now, if you want to melt something, you add energy, so that would be a positive value. But you're freezing something, so you're removing energy from the system, so it should be negative. So even though the number doesn't have a negative, we add 1 to it. So about 500,000. So final step, the last step right here, which is also quite easy. So this is MC delta T again, but be careful. We are no longer in water stage. We're at ice stage. So that has to be the specific heat for ice, not for liquid water. So if you remember how much that was, that's good. If you don't, go to the specific heat, the C table, not the latent heat table, look it up. It's about 2000-ish. I remember 2090 joules per kilogram per degree Celsius. I'm just gonna that per kilogram degree Celsius. There you go. And then what's the change in temperature? So I am at 0 degree, I want -10. So the change in temperature is final temperature minus initial temperature, which is -10, right? It's just -10. So this one naturally gives us a -2, which we don't even have to worry about adding this one, not that much. 31,350 joules. I mean, compared to the other two, it's not that much, right? So then we add them all together. So total heat energy removed. So total heat removed. One moment. Total heat removed is about 6.58 times 10 to the 5 joules. So about 658,000 joules of energy in total. So these are from number. Now, I guess the reason why I didn't put negative is because I used the word removed, right? So I can say I removed $5,000 from my bank account. And so I say, I don't say I removed -$5,000, right? I removed $5,000. So if you say the word remove, then you don't really have to put the negative in front. So that's it. Okay, goodbye.